She's going to show you her black bottom. Way down in South in Alabama, I got a friend to call.
Our goal in this video is to finish up the material of section 13.1 of Dummett and Foote. And in order to do that, we're going to start with a discussion about homomorphisms on polynomial coefficients. So here's the idea. Suppose sigma is any homomorphism of fields. Then sigma extends to a homomorphism of the polynomial rings f bracket x to f prime bracket x as follows. So I'm going to show you how this sigma, this homomorphism from f to f prime, gives this homomorphism of these polynomial rings. We're going to take a polynomial f of x, which has coefficients cn x to the n plus cn minus 1 plus c1x plus c0. So these ci's are in your field f. And we're going to define sigma of f is going to be a polynomial in f prime bracket x. So sigma of f of x is going to be the polynomial we get by just applying sigma to each of the coefficients defining f. So sigma of cn times x to the n plus sigma of c1 times x plus, oh, this should be sigma of c0. Okay, so I want to point out that I am using the same symbol sigma for this homomorphism of fields and for the homomorphism that we get between polynomial rings. So this homomorphism is going to be called applying sigma to the coefficients. So I'll come back and say a little bit about why this is a homomorphism, what you need to do to check in a few minutes. But first I want to say what happens when you apply this homomorphism, this applying sigma to the coefficients homomorphism, to f evaluated at some element in your field. So, okay, we have an element of f. We can take our polynomial in f bracket x, and we can evaluate it and get some element of f, right? So f of alpha is some element of f. So we can apply sigma to it, sigma being this homomorphism from f to f prime, and sigma of f of alpha is going to be some element of f prime. And the question that we want to understand is this should be related to the polynomial sigma of f, which is in f prime bracket x, evaluated somewhere. So let's look and see what happens. So sigma of f of alpha, well, f of alpha is just cn alpha to the n plus c1 alpha plus c0. If we apply sigma here, this is a homomorphism. So here's some elements in a field that this is sigma of cn alpha to the n plus sigma of cn minus 1 alpha to the n minus 1 plus sigma of c1 alpha plus sigma of c0. And then each one of those terms has a ci coefficient and an alpha to the I term. So because sigma is a homomorphism, what we get is sigma of cn times sigma of alpha to the n plus sigma of cn minus 1 times sigma of alpha to the n minus 1 plus sigma of c1 times alpha times sigma of alpha plus sigma of c0. And okay, what is sigma of alpha to the I? Well, this is a homomorphism. So it's sigma of alpha times sigma of alpha times sigma of alpha I times. So all we're doing here is rewriting each sigma alpha to the I as sigma alpha to the I. And now it's clear that what we're getting is this polynomial sigma of f of x evaluated at, well, here we have x to the n, and here we have sigma of alpha to the n. So what we're getting here is sigma of f evaluated at sigma of alpha. So this is the thing that I want to emphasize, is that you might at first think that sigma of f of alpha is just sigma of f evaluated at alpha, but that doesn't even make sense because sigma of f is an element in f prime bracket x, and alpha is an element of f. So alpha might not even be in f prime. So it really is sigma of f evaluated at sigma of alpha. All right, so what happens in the case that alpha is a root of f? Then what we see is that f of alpha is 0. So sigma of f of sigma of alpha is sigma of 0. Right? It's sigma of 0 in here. So that's 0 because sigma is a homomorphism from f to f prime. So it sends 0 to 0. So what does that mean? So sigma sends so if you have alpha being a root of f, then what we're seeing is sigma of alpha is a root of sigma of f. So sigma sends any root of f of x in f. So it sends some element in f alpha that is a root of f of x to a root sigma of alpha of this polynomial sigma of f of x in f prime. So by doing this calculation, we're seeing that the original homomorphism of fields, f to f prime, sends roots of f to roots of sigma of f. Okay, so here I said that this extends to a homomorphism of polynomial rings, but I didn't actually prove that. So what do you have to check? So you have to check that sigma of f plus g is the same thing that you get when you take sigma of f plus sigma of g. I haven't written the of x's here for space reasons. You have to check that sigma of f times g equals sigma of f times sigma of g. And if you prefer for all of your ring homomorphisms to send 1 to 1, you should check that sigma of 1 is also 1 in these polynomial rings. And each one of these things is straightforward to check, just using the definition of what it means to apply sigma to the coefficients. So I'll leave these details for you to check. It's easy to see, just looking at f of x compared to sigma of f of x, that sigma preserves degrees, right? Because this is a homomorphism of fields. If Cn is not 0, sigma of Cn is not 0 either. And it preserves the property of being monic. So if Cn equals 1, then sigma of Cn has to be 1 as well. All right, so what do we know? If f splits completely in f bracket x, then what happens when you apply the coefficient sigma to the coefficients? Well, sigma sends linear factors to linear factors. So the factorization that you have in f bracket x is going to be preserved by applying sigma to the coefficients. So sigma of f is going to split completely in f prime bracket x as well. So again, I'll leave you to think about the details here, but polynomials that split completely get sent to polynomials that split completely. All right, so I'm going to pause and erase, and I'm going to give an example involving one particular homomorphism of fields. I'll give an example where your homomorphism goes from the complex numbers to itself and comes from complex conjugation. And then I'll focus in general on the case that really is of interest right now, which is when sigma is not just a homomorphism of fields, but is actually an isomorphism. Let's give an example of this applying sigma to the coefficients homomorphism. Complex conjugation is an automorphism of C. So it's an isomorphism from C to itself. If, I'm missing a letter here, if f of x is in C bracket x and alpha is an element in C, then what we've just seen is that if we take f of alpha and then apply this homomorphism, complex conjugation, it's the same thing as if we take the conjugate of f and apply that to the conjugate of alpha. So that's saying that sigma of f of alpha is equal to sigma of f applied to sigma alpha. Okay, so this is where this conjugate of f is the polynomial in C bracket x that we get by taking the complex conjugate of each coefficient of f of x. So what if f of x is a polynomial in C bracket x, but the coefficients are all actually in R? what's special about R is these are the elements in C that are fixed by complex conjugation. So if f of x has real coefficients, that means that the conjugate of f is the same as f. So in particular, if you take f of alpha and take the complex conjugate, that's the same as if you take f of alpha conjugate. So that means that if alpha is a root of f of x, that means that f of alpha equals 0. So the conjugate of f of alpha is 0. Then f of the conjugate of alpha is 0 also. So the roots of polynomials with real coefficients are either real or they come in these complex conjugate pairs. Okay, so the special case of the discussion that we started with in this video that we want to focus on is this example is one instance of it. It's where sigma is not just a homomorphism between fields, but is actually a field isomorphism. In this case, we know that sigma extends to this homomorphism of polynomial rings, but if sigma is a field isomorphism, then it extends actually to a ring isomorphism. Why is that? Well, we know it's a homomorphism, so we just have to show that it's bijective. So why is this an isomorphism? Because it has an inverse. So what is the inverse? It's the homomorphism from f prime bracket x back to f of x that is applies sigma inverse to the coefficients. So since sigma is a field isomorphism, it has an inverse, sigma inverse, so we can take the corresponding ring homomorphism going the other way. Okay, so now let's focus on the setting that's been most relevant to us in our discussion of fields so far, where we have a field f, we have a polynomial p of x in f bracket x that is irreducible. So why is this so relevant? Because we've been thinking about extensions of f that come from f bracket x mod the ideal generated by p of x. So what happens if we apply sigma to the ideal generated by p of x? Well, we have this ring isomorphism. The ideal generated by p of x is a maximal ideal. So this ring isomorphism takes it to some other maximal ideal over on this side, f prime of x, in f prime of x. So this is a maximal ideal in f prime bracket x in this polynomial ring. Think about what is this ideal? Like, what are the polynomials that are in it? And you'll see that it is everything in f prime bracket x that's divisible by this one polynomial, sigma of p of x. So it's the ideal generated by sigma of p of x. But if this is a maximal ideal, that's telling us that sigma of p of x is an irreducible polynomial in f prime bracket x. So we can consider these two fields, f bracket x mod the ideal generated by p of x, and f prime bracket x mod the ideal generated by sigma of p of x. These are each fields because we're taking the quotient by maximal ideals. These maximal ideals are related to each other. This ring isomorphism sends one of them to the other. And these quotient fields are isomorphic. What is the isomorphism? Well, we have to say, where do you send a coset in of the ideal generated by p of x in f bracket x? Where do you send that over here? So let's take the coset of the ideal generated by p of x containing f of x, and we're going to send it to the coset of sigma of p of x, the ideal that generates, containing the polynomial sigma of f of x. And it's straightforward to really carefully check that this actually is an isomorphism. Okay, so where are we? In the last lecture, we talked about how this field, which we showed, is an extension of f in which the polynomial p of x has a root, is connected to f adjoin alpha, where alpha is an element of some extension that is a root of p of x. So we can apply that idea over here and also over here. So I'm going to pause and erase, and I'll tell you the conclusion of this discussion. So where are we? We have these two fields, f bracket x mod the ideal generated by p of x, and f prime bracket x mod the ideal generated by this irreducible polynomial sigma of p of x. And we know that they're isomorphic to each other. So theorem 6 from last time was all about isomorphisms between fields that look like this one and fields of the form f adjoin alpha, where alpha was some root of the polynomial p of x that was contained in some extension of f. So theorem 6 from last time tells us that f adjoin alpha is isomorphic to this field. And what does the isomorphism look like? Well, how do you think of elements of f adjoin alpha? They're polynomials in alpha. So you have some polynomial in alpha. Where do you send that? You send that to the coset of the ideal generated by p of x containing this polynomial f, now not f of alpha, but f of x. Same thing over on this side. We have this field, f prime bracket x mod the ideal generated by sigma of p of x is isomorphic to f of beta, f adjoin beta, where beta is a root contained in some extension of f prime of the irreducible polynomial sigma of p of x. So what does that isomorphism look like? Well, you just take this coset of the ideal generated by sigma of p of x containing this polynomial sigma of f of x. And what do elements of f adjoin beta look like? They're polynomials in beta. So you send this coset to the polynomial sigma of f of beta. Okay, so this is all described nicely as theorem 8 in section 13.1, which we've already proven now. It says, let alpha be a root of p of x contained in some extension of f, and beta be a root of sigma of p of x contained in some extension of f prime. Then there is an isomorphism taking f adjoin alpha to f prime adjoin beta, such that this isomorphism sends alpha to beta. And when you take this isomorphism and you restrict it to f, what do you get? You get this sigma, this original isomorphism from f to f prime that got this whole thing started. So what's the one part that we haven't proven yet? Well, what is this isomorphism psi? It's just the composition of all of these isomorphisms. So you start with f of alpha, and it eventually gets sent to sigma of f of beta. And what we haven't checked yet actually is that this isomorphism restricted to f actually is sigma. So where is f contained in f adjoin alpha? Well, the elements of f adjoin alpha are these polynomials in alpha, and we get a copy of f inside of here as the polynomials that are degree 0 in alpha. So you just have to check that if the polynomial f of alpha is actually just some element a in f, where does it get sent? Well, it gets sent to a plus the ideal generated by p of x, which gets sent to sigma of a plus the ideal generated by sigma, this coset of sigma of p of x, which just gets sent to the corresponding polynomial in beta, but it's just this single constant sigma of a. So that's easy to check, and that finishes the proof of this theorem. So what I want to emphasize here is that this theorem really is stronger than saying that f adjoin alpha and f prime adjoin beta are isomorphic. Because what it's saying is they're isomorphic, but there's a particular choice of isomorphism that sends alpha to beta, and it gives you back this particular isomorphism sigma between f and f prime that you started with when you take the isomorphism and restrict it to your subfield f inside of f adjoin alpha. So there's this helpful picture in Dummeted Foot that I'm repeating here that will be useful. This result is going to be useful when we talk more about Galois theory. So what's going on is we have these four fields, f, f prime, and then for f and f prime, for each one we have an extension, f adjoin alpha, f prime adjoin beta, and sigma is this isomorphism going this way, and psi is this isomorphism going this way. And if you restrict psi down to the bottom, you exactly get sigma. Okay, So we'll come back to this and use this when we talk about Galois theory, but we're also going to come back to this idea of homomorphisms on polynomial coefficients when we talk about splitting fields, and in particular when we prove that any two splitting fields for the polynomial p of x are isomorphic to each other.